Betelgeuse. You're at your desk. It's December 2019. The alert comes in quietly. No alarm, no fanfare, just a number that doesn't belong. Betelgeuse is dimming. Not slightly, not within the expected range. 60%. The star that has burned in the shoulder of Orion for 10 million years is fading. You check the instruments. The instruments are fine. You check the calibration. The calibration is fine. The star is wrong. Betelgeuse, one of the largest stars in the observable sky, a red supergiant so enormous it would swallow every planet from Mercury out past Jupiter if placed at the center of our solar system, is doing something no one has seen it do before. The data is clean. The problem is real. Something is happening 850 light-years away, and you are watching it happen in real time. Here's what makes this impossible to simply dismiss. Betelgeuse had been observed behaving oddly for years before 2019. It pulses. It breathes. It has a roughly 420-day cycle of expansion and contraction, a slower, roughly 5.9-year cycle layered beneath that, and irregular convective surges that make its surface look, under high-resolution imaging, less like a star and more like a boiling ocean the size of the inner solar system. Astronomers had classified these as normal. Massive red supergiants are violent places. This was understood. What was not understood was what happened between October 2019 and February 2020, a period now documented across dozens of peer-reviewed papers and known collectively as the Great Dimming. The brightness drop was measured systematically by Edward Guinan and Richard Wasatonic at Villanova University, who had been monitoring Betelgeuse through the American Association of Variable Star Observers for years. Their observations, published in the Astronomer's Telegram in December 2019, confirmed what amateur and professional astronomers worldwide were simultaneously recording. Betelgeuse had fallen to a visual magnitude of approximately 1.6, its faintest recorded measurement in over a century of systematic observation. That is not a rounding error. That is a star fading to 60% of its normal luminosity in a matter of weeks. The Hubble Space Telescope was redirected. Observations taken in January and February 2020 by Andrea Dupree at the Center for Astrophysics, Harvard and Smithsonian, revealed something extraordinary. A dense plume of material, hot plasma, superheated to between 3,000 and 4,000 Kelvin, had erupted from the southern hemisphere of the star and was moving outward. As it cooled, it condensed into dust. A curtain of dust, a cloud larger than the distance from Earth to the Sun, had formed between Betelgeuse and every telescope watching it. The star had not dimmed. It had hidden. The standard cosmological model says this is consistent with known red supergiant behavior. Massive convective cells on stars like Betelgeuse periodically eject material into the surrounding envelope. The star's outer layers are loosely bound compared to smaller stars, held against escape by a gravitational field spread across a radius of approximately 950 solar radii. Surface mass ejections, while dramatic, are categorized as ordinary stellar weather events. Betelgeuse will continue to pulse and erupt for roughly 100,000 more years before exhausting its core fuel and collapsing into a supernova. The Great Dimming, under this interpretation, was an extreme but explainable event. Dust formed, light was blocked, the star recovered. But the data doesn't stop there. In the aftermath of the Great Dimming, the Atacama Large Millimeter Array in Chile and the Very Large Telescope in the Atacama Desert captured something the dust explanation alone cannot account for. The convective motion on the surface of Betelgeuse is profoundly, inexplicably asymmetric. On a star of this size, theoretical models predict that convective cells, those churning columns of rising hot plasma and falling cool plasma, should distribute themselves across the surface in rough statistical balance. They do not have to be perfectly symmetric, but they should exhibit global behavior that stellar interior models can reproduce. They do not. Observations published in Nature Astronomy in 2021 by researchers including Jingze Ma and collaborators revealed that single convective cells on Betelgeuse can span up to 60% of the star's visible disk. One cell, 60% of a disk, nearly 2 billion kilometers across. This is not a local disturbance. This is a structural phenomenon that current stellar models, even those incorporating three-dimensional radiation hydrodynamic simulations, cannot fully replicate. Some astrophysicists suggest that Betelgeuse may be further along in its nuclear burning sequence than previously estimated. that helium shell burning or even more advanced fusion stages may be altering the internal pressure gradients in ways that drive anomalous convection asymmetry. A minority of researchers propose that the star's rotation, which appears to be faster than expected for its age, may be interacting with its convective envelope in ways that current magnetohydrodynamic models are not equipped to describe. What no model fully explains is the combination, the ejection event, the asymmetric convection, the anomalous rotation, all occurring together, all at once. Is Betelgeuse closer to collapse than we think? Does its asymmetric convection reveal a gap in our understanding of how massive stars age? If a single convective cell can span a structure 2 billion kilometers wide, what does that mean for the physics we use to model stellar interiors everywhere? And when this star finally does collapse, in an event bright enough to cast shadows on Earth at noon, will it behave the way our models predict? The universe does not announce what it is about to do, it only shows you the signals, and from somewhere in the Large Magellanic Cloud, 160,000 light-years away, a star is sending a signal that makes Betelgeuse look almost ordinary. R136A1. You are standing inside the data, in a manner of speaking. It is 2010. The Very Large Telescope at the Paranal Observatory in the Atacama Desert of Chile is feeding its output to Paul Crowther, an astrophysicist at the University of Sheffield, and he is looking at a number that his instruments keep confirming and his physics keep rejecting. The number is a mass, a stellar mass, and it is a mass so far beyond what the universe is supposed to permit that Crowther will later describe the experience of verifying it not as excitement, but as a specific, prolonged discomfort, the feeling of being certain you are right about something the laws of nature have ruled out. The star is called R136A1. It lives at the molten core of the star cluster R136, inside the Tarantula Nebula, inside the Large Magellanic Cloud, a satellite galaxy to our own Milky Way, at a distance of approximately 160,000 light-years from Earth. To grasp that distance even approximately, light, traveling at 300,000 kilometers per second without pause or deviation, would require 160,000 years to make the journey from there to here. The photons Crowther was analyzing when he found the impossible number left their source before anatomically modern human beings existed on this planet. And what those ancient photons described was this: a star currently estimated at 265 solar masses. Here's what makes this impossible. Crowther and his collaborators published their findings in the monthly notices of the Royal Astronomical Society in 2010. The paper laid out the measurements derived from ultraviolet spectroscopy, collected using the Hubble Space Telescope's Space Telescope Imaging Spectrograph, alongside the Very Large Telescope's SINFONI and MAD instruments. The analysis was painstaking and methodologically conservative. The team wasn't looking for a record. They were trying to map the mass distribution of one of the most extreme star-forming regions in the observable universe, and R136A1 simply refused to fit the expected range. Subsequent observations, including revised analyses published as recently as 2022 using newer Hubble ultraviolet data, have refined the figure but not deflated it. 265 solar masses, give or take tens of solar masses in either direction, still impossible either way. The theoretical ceiling for stellar mass is called the Eddington limit, named after Sir Arthur Eddington, the British astrophysicist who formalized it in the 1920s. The limit describes the precise point at which the outward radiation pressure from a star's luminosity equals the inward gravitational force holding it together. Exceed that equilibrium, the physics says, and the radiation wins. The star tears itself apart. It blows its own outer layers away faster than they can be replenished. The universe, in other words, has a built-in mechanism for preventing stars from getting too large. Based on current stellar physics, that ceiling sits somewhere between 100 and 150 solar masses, depending on the metallicity of the stellar environment and the modeling framework being used. R136A1 is between 30 and 60 solar masses above that ceiling, not near the edge, not grazing it, comfortably, inexplicably beyond it, shining at approximately 8.7 million times the luminosity of our Sun, with a surface temperature of approximately 46,000 Kelvin, a temperature so extreme that the star emits the overwhelming majority of its energy not as visible light, but as ultraviolet radiation and beyond, wavelengths the human eye cannot perceive, and that Earth's atmosphere screens out before they ever reach the ground. The standard cosmological model says that stars near or above the Eddington limit shed mass so aggressively through stellar winds and radiation-driven outflows that they regulate themselves downward. The star loses mass almost as fast as it can accumulate it, functioning as its own governor. This is not a fringe concept. It is central to our understanding of how the most massive stars in the universe live and die, and it is supported by extensive observational and theoretical work across decades. But the data from R136A1 does not support a star that has been quietly shedding its way down to a permissible number. Some astrophysicists suggest that R136A1 may have formed through stellar mergers, that two or more already massive stars collided and combined in the dense, chaotic environment of R136's core, producing a single object that bypassed the normal accretion and regulation pathway entirely. This would technically sidestep the Eddington limit rather than violate it. A minority of researchers propose that in sufficiently metal-poor, high-density star-forming regions, conditions in the early stages of stellar formation may permit mass accumulation to proceed faster than radiation pressure can respond, briefly opening a window above the theoretical ceiling before feedback mechanisms engage. Both explanations preserve the underlying physics. Both require assumptions that have not been confirmed by direct observation, and both leave several things unexplained. Why is R136A1 still there? A star of this mass, under our best models, should be so violent in its stellar wind output that it should be visibly, dramatically destroying itself on a timescale of millions of years. And yet it persists. Why does the star cluster R136 contain not one, but several stars crowding or exceeding the theoretical upper mass limit, suggesting this is not an isolated fluke, but a pattern? Why does the universe produce conditions under which its own rules appear to bend? What does it mean when the upper limit of what can exist is not a wall but a suggestion? And if our physics cannot correctly predict the maximum size a single star can reach, what else about stellar formation are we getting wrong? Something almost as disquieting waits in the next entry. Not a star that is too massive to exist, but a star that seems to be disappearing in ways that have no name yet. KIC 8462852. You are staring at a light curve. It is September of 2015, and you are a citizen scientist, one of thousands who volunteered their time to a project called Planet Hunters, a collaboration run through the Zooniverse platform that lets ordinary people sift through data from the Kepler Space Telescope looking for the tiny, regular dips that signal a planet crossing its star. You have looked at thousands of these curves. You know what they look like. A small, clean notch, symmetrical, predictable, the same depth every time, the same duration. This is not that. The star designated KIC 8462852 sits roughly 1,480 light-years from Earth in the constellation Cygnus. That distance means the light you are looking at left this star around the time the Byzantine Empire was still standing. You are not looking at the present. You are looking at a message from the early medieval period, finally arriving. And that message is deeply, structurally wrong. The dips you are seeing drop the star's brightness by up to 22%. A Jupiter-sized planet, the largest category of planet we know, would block roughly 1% of a star's light, maybe 1.5. 22% requires something enormous, something the width of a significant fraction of the star itself. But that is only the beginning of what makes this strange. The dips are irregular. They come without schedule. They are asymmetric. They fall faster on one side than the other, the profile jagged and uneven in ways that no spherical orbiting body would produce. There are shallow dips and catastrophic ones, and clusters of dips overlapping each other like interference patterns in water. And between those dips, the star itself has been gradually dimming over time, losing roughly 3% of its total brightness over the span of a century, according to analysis of archival photographic plates reviewed by researchers at Louisiana State University. Tabitha Boyajian, then at Yale University, led the formal analysis of this star, publishing the findings in the monthly notices of the Royal Astronomical Society in 2016. The paper immediately captured public attention because Boyajian and her collaborators were direct about something unusual for a scientific publication. They could not find a natural explanation that fit all the data simultaneously. The star became known, quickly and permanently, as Tabby's star. Here's what makes this impossible. The Kepler Space Telescope monitored this star with extraordinary precision over 4 years of continuous observation between 2009 and 2013. Kepler was designed to detect brightness changes as small as 84 parts per million. The changes in KIC 8462852 were not subtle. They were enormous, repeated, and followed no pattern that orbital mechanics could produce. The deepest single dip event, observed in 2011, reduced the star's brightness by 22% over a period of roughly 192 days, then partially recovered, then dipped again in a complex overlapping cascade that resembled nothing in any existing catalog of stellar behavior. The standard cosmological model says stars dim when something passes between them and the observer. The dimming follows predictable geometry. A planet produces a flat-bottomed symmetric transit. A disk of dust produces a gradual, wavelength-dependent fade. Shorter wavelengths scatter more, so a dust cloud dims blue light more than red. A swarm of comets, the most popular natural candidate, produces a cluster of overlapping transits from many bodies traveling in related orbits. Each of these explanations accounts for some portion of what Kepler saw. The comet swarm hypothesis, advanced in part by Jason Wright at Pennsylvania State University and discussed seriously in the literature, can explain the irregular clustering. Circumstellar dust can explain the long-term secular dimming. These are legitimate, considered explanations advanced by serious researchers. But the data doesn't cooperate fully with any single one. A comet swarm large enough to block 22% of a star's light would require a quantity of cometary material that strains credibility. Billions of comets, concentrated in a geometry that produces asymmetric, non-repeating transits. And follow-up observations of the star's behavior at multiple wavelengths, including analysis by Huan Meng and collaborators published in the Astrophysical Journal in 2017, showed that the dimming is wavelength-dependent in ways consistent with dust, but the dust scenario struggles to explain the rapid, deep, irregular dips without invoking dust structures of implausible density and configuration. No single natural model has been proposed that accounts simultaneously for the magnitude of the dips, their asymmetry, their irregularity, their non-repetition, and the long-term secular fade. Some astrophysicists suggest the star may be undergoing internal structural changes we do not yet have a framework for. A minority of researchers, including Wright himself, in a now famous note, raised, carefully, with full scientific hedging, the possibility that artificial megastructures of extraterrestrial origin could produce exactly this kind of signal. That hypothesis has not been confirmed. It has also not been eliminated. What is passing in front of this star? Why does the geometry of each dimming event look different from the last? Why has this star been growing slowly, steadily darker for over a century? If it is dust, where is the infrared signature a warm dust cloud should produce? And if something vast enough to swallow 22% of a star's light is orbiting 1,480 light-years away, what built it? Something far stranger than megastructures, though, may be hiding much closer to home, in a star so ancient it should not be possible for it to exist at all. HD 140283. You are standing at a window, not a metaphorical window, a literal one, in the hallway of the Space Telescope Science Institute in Baltimore, Maryland, sometime in early 2013. It is late. The building is mostly quiet. A colleague has just handed you a printed summary of new parallax measurements taken by the Hubble Space Telescope's fine guidance sensors, and you are reading the same line for the third time because it will not resolve into something sensible no matter how many times your eyes cross it. The star is older than the universe. Not by a rounding error. Not by some slight miscalculation that falls within a comfortable margin. The number on that page says 16 billion years. The universe is 13.8 billion years old. You are holding a document that claims to have found something that existed before existence had a beginning. You put the paper down. You pick it up again. The number has not changed. This is the exact position Howard Bond, an astronomer with the Space Telescope Science Institute and a researcher with decades of stellar astrophysics behind him, found himself in when he led the team that published revised distance and age measurements for HD 140283 in the journal Astrophysical Journal Letters in February of 2013. The paper was careful. It was precise. It was also, quietly, one of the most destabilizing documents in modern cosmology. HD 140283 sits approximately 190 light-years from Earth, practically in our backyard by cosmic standards. You could, If you could travel at the speed of light, reach it in 190 years. It sits in the constellation Libra, visible to amateur telescopes, a dim subgiant star that has been catalogued and observed for over a century. Its metal content is extraordinarily low, a metallicity of roughly -2.4 on the logarithmic astronomical scale, meaning it contains only about 1/400th the iron abundance of our own Sun. This is important. Stars formed in the early universe, before successive generations of stellar explosions had seeded the cosmos with heavier elements, are metal poor. HD 140283 is one of the most metal-poor stars ever found near our solar system. In that sense, it has always looked ancient. Nobody expected it to look quite this ancient. Bond's team used the Hubble Space Telescope's fine guidance sensors to measure the star's parallax with extraordinary precision, establishing its distance at 190.1 light-years with an uncertainty of just 0.6 light-years. From that refined distance, they back-calculated the star's luminosity, which then fed into stellar evolution models to determine its age. The initial result, 16.3 billion years, with an uncertainty range that, even at its most optimistic lower bound, placed the star at 13.9 billion years old, 100 million years older than the universe itself. Subsequent refinements, incorporating revised measurements of oxygen abundance, updated nuclear reaction rates, and adjusted helium diffusion models, brought the central estimate down to 14.46 billion years, still sitting, uncomfortably, 660 million years above the age of the universe, as established by the European Space Agency's Planck satellite, which fixed cosmic age at 13.799 billion years based on measurements of the cosmic microwave background. Here's what makes this impossible. Stars do not form before the universe that contains them. The Big Bang produced hydrogen and helium. Stars are made from that material. No star can be older than the process that created the atoms inside it. This is not a philosophical argument. It is a statement of physical causality. And yet here sits HD 140283, 200 light-years away, apparently predating its own origin. The standard cosmological model says this is a measurement problem, not a physics problem. Uncertainties in stellar evolution modeling, particularly around helium diffusion rates, convective overshoot, and the precise oxygen-to-iron ratios in the star's atmosphere, introduce enough flexibility that the true age, with all errors properly accounted for, could fall just below 13.8 billion years. The error bars on Bond's own estimate extend downward to 13.2 billion years. At that value, the star is old but not impossible. The universe would have formed it within its first 600 million years, extremely early but not prohibited. But the error bars extend upward as easily as they extend downward, and the central estimate has not moved below 14 billion years across a decade of increasingly refined measurements. Some stellar astrophysicists suggest that systematic errors in our distance measurement techniques, even with Hubble parallax data of this precision, could account for the discrepancy. Others propose that uncertainties in the cosmological constant, the value driving the universe's expansion rate, leave enough flexibility in the age of the universe itself that the conflict may be smaller than it appears. The Hubble tension, the ongoing dispute between competing measurements of the universe's expansion rate, means that the universe's age may not be as precisely pinned down as the Planck data suggests. But none of this explains a star sitting 190 light-years away that, by every measurement we know how to make, appears to have begun its life before time had a beginning. How can a star be older than the universe that made it? If our stellar evolution models are wrong at this scale, what else are they wrong about? Does HD 140283 reveal a flaw in how we understand stellar aging, or a flaw in how we understand cosmological time itself? And if the universe is somehow older than we believe, what reshaped the evidence to make it look younger? The oldest known star near our solar system raises questions that no currently accepted model can answer cleanly, and the universe's capacity for the inexplicably violent is only beginning to come into view as we turn next to an object whose magnetic field is strong enough to rewrite the laws of matter itself. SGR 1806-20. You are not in space. That's the part that should unsettle you most. You are standing on Earth. You are inside the atmosphere. You are 50,000 light-years away from what is about to happen, 50,000 years of light travel between you and the source, and it still reaches you, not as a faint whisper detectable only by the most sensitive instruments humanity has ever built, not as a trace chemical signature in ice cores, decoded centuries later. It reaches you as a physical event, The ionosphere above your head, the charged shell of atmosphere that bounces radio waves and makes long-distance communication possible, briefly lights up as if a star has gone off next door. It is December 27th, 2004. It is 06 hours 44 minutes at Universal Coordinated Time, and something 50,000 light-years away in the constellation Sagittarius has just done something that the known laws of physics have no comfortable place for. The event lasted 0.2 seconds. In that interval, SGR 180620 released more energy than our sun will produce in 250,000 years. Let that sit for a moment. The sun has been burning for 4.6 billion years. It will burn for approximately another 5 billion. In the full span of its existence, 9.6 billion years of nuclear fusion at its core, converting 4 million metric tons of hydrogen into energy every single second. The total output of our parent star across its entire lifetime does not approach what SGR 180620 released in a fifth of a second. Not even close. Here's what makes this impossible. The object in question is a magnetar, a specific and extraordinarily rare class of neutron star. Neutron stars are already among the most extreme objects in the universe that we can actually verify exist. When a star between roughly 8 and 20 solar masses exhausts its fuel and collapses, the resulting remnant is a sphere approximately 20 kilometers across, smaller than most mid-sized cities, containing mass equivalent to 1.4 to 2 solar masses compressed to nuclear density. A teaspoon of neutron star material weighs approximately 4 billion metric tons. These are objects where gravity has crushed matter past any state achievable in a terrestrial laboratory. Magnetars go further. They are neutron stars with magnetic fields so powerful that they stress space itself. The magnetic field of SGR 180620 has been measured at approximately 1.6 times 10 to the 15th power Gauss, roughly 1 quadrillion times the strength of Earth's magnetic field. At such field strengths, the vacuum of space becomes birefringent. Photons of different polarizations travel at different speeds. These fields are so intense they would strip the iron from hemoglobin in your blood if you were within 1,000 kilometers of the surface. The outburst of December 27, 2004, was catalogued and studied by an international network of high-energy space observatories, including the Ramati High-Energy Solar Spectroscopic Imager, operated by the National Aeronautics and Space Administration, the High-Energy Transient Explorer 2, the Integral Gamma-Ray Telescope operated by the European Space Agency, and the Rossi X-ray Timing Explorer. Researchers Brian Gainsler of the Harvard-Smithsonian Center for Astrophysics, Kevin Hurley of the University of California at Berkeley, and an international collaboration published detailed analyses in Nature in 2005. The peak luminosity of the initial spike was calculated at approximately 2 times 10 to the 47th ergs per second. The total energy released in the first 0.2 of a second exceeded 10 to the 46 ergs. For reference, a typical supernova, the complete explosive destruction of a massive star, releases approximately 10 to the 51 ergs over several seconds. The flare was brief, but its instantaneous luminosity during those 0.2 of a second exceeded the luminosity of a supernova. The standard cosmological model says this is explainable within known physics. Magnetars accumulate magnetic stress over time, deforming the rigid crystalline crust of the neutron star until the crust fractures, a starquake, releasing the built-up magnetic energy in a sudden cascade. The mathematics of magnetohydrodynamics, when applied to objects with field strengths at this scale, does permit energy releases of this magnitude. The model is internally consistent. The physics, while extreme, does not formally require anything outside established frameworks. This is a known class of object doing a known type of thing, only at a scale that happens to be staggering. But the data raises questions that the starquake model does not resolve cleanly. The total energy released, integrated across the full event, appears to exceed what the available magnetic energy budget of the star should permit, even under generous estimates of the internal field configuration. Some astrophysicists suggest that the emission mechanisms coupling the magnetic field to the radiation output are not fully understood, and that our models of neutron star interiors contain significant uncertainties at these densities. A minority of researchers propose that phase transitions in quark-gluon matter at the core, a state of matter we have never directly observed, could contribute energy outputs beyond what standard neutron star models predict. What we know is what the instruments recorded. The rest is inference. What is actually happening inside the crust of a magnetar at the moment of a giant flare? How is energy transferred from the magnetic field to the radiation field at efficiencies that appear to exceed our models? If this event had occurred at 1/10 the distance, would it have been capable of stripping Earth's ozone layer? How many magnetar giant flares have occurred in the history of the galaxy that we simply were not watching for? And what does it mean that an object the size of a city, 50,000 light-years away, can reach down through the vacuum of space and physically alter our atmosphere without warning? Somewhere else in the galaxy, a different kind of star is doing something impossible for entirely different reasons. And the periodic table may never be the same again. Przybylski's star. You are holding a piece of paper that should not exist. It is 1961. You are at Siding Spring Observatory in New South Wales, Australia, and the spectrograph trace in your hands, fresh from the instrument, still faintly chemical smelling, shows element lines that belong to no normal star. Antoni Przybylski, a Polish-Australian astronomer working at the Mount Stromlo and Siding Spring Observatories, is looking at the same lines. He has been trained to read stellar spectra the way a doctor reads an electrocardiogram, a steady rhythm of iron, calcium, sodium, the familiar grammar of nuclear fire. What the spectrograph is showing him instead is something closer to a ransom note. The lines are wrong, the elements are wrong, not subtly wrong, catastrophically, inexplicably wrong. The star designated HD 101,065 sits approximately 370 light-years from Earth in the constellation Centaurus. It is, by most photometric measures, unremarkable. A slowly pulsating app star, meaning a chemically peculiar A-type star with an effective surface temperature of approximately 6,750 Kelvin and a luminosity roughly 40 times that of the Sun. Nothing in its position, its brightness, or its motion across the sky suggests it is about to overturn assumptions about how stars work at a chemical level. And then you look at what it is made of. Iron is nearly absent. Nickel is nearly absent. The lighter elements that form the backbone of stellar nucleosynthesis, the elements a star is supposed to forge and display, are suppressed to the point of near invisibility. In their place, Przybylski's star is saturated with some of the heaviest, rarest, most exotic elements on the periodic table: holmium, gadolinium, terbium, dysprosium, rare earth elements present in concentrations so extreme they defy the standard model of stellar chemistry. Subsequent spectroscopic analysis by Simon Cowley and colleagues, published in the journal Publications of the Astronomical Society of the Pacific in 2004, pushed the mystery further into territory that serious researchers found genuinely difficult to write about in measured academic prose. The spectrum contains what appear to be absorption lines consistent with actinium, protactinium, and einsteinium. Here's what makes this impossible. Actinium-227 has a half-life of 21.77 years. Protactinium-231 has a half-life of 32,500 years, which sounds long until you hold it against the billions of years this star has existed. Einsteinium-254, and this is the one that makes physicists pause mid-sentence, has a half-life of 276 days, less than a year. This is not a stable element hiding in a stellar atmosphere. This is an element that is actively, continuously decaying. For Einsteinium to appear in a spectrum at all, it must have been produced recently. Not recently in cosmological terms. Recently, as in, it is being made right now, or it was made within the last handful of years, because any older sample would simply no longer exist in detectable quantities. The standard cosmological model says that elements heavier than iron are produced through neutron capture processes, the slow S process occurring in asymptotic giant branch stars over millions of years, and the rapid R process occurring in the extreme environments of neutron star mergers and supernovae, events of staggering violence that seed the surrounding galaxy with heavy element debris. This model is well supported, mathematically rigorous, and confirmed by the spectroscopic signatures of thousands of stars and by the gravitational wave observations of neutron star mergers. A chemically peculiar app star can, under this model, accumulate anomalous surface abundances through atomic diffusion, the slow gravitational settling of heavy elements toward the core and the radiative levitation of others toward the atmosphere, which can concentrate certain rare earth elements to visible levels over stellar timescales. But atomic diffusion cannot produce transuranic elements with half-lives measured in months. Radiative levitation cannot manufacture Einsteinium from nothing. A process that concentrates what already exists cannot explain the presence of something that decays faster than a human child learns to walk. Whatever is making these elements, it must be operating continuously, inside or around this star, at this moment, and it must be operating at an energy and neutron flux that current stellar physics does not assign to a quiet, slowly pulsating A-type star 370 light-years from here. Some astrophysicists suggest the star may harbor some exotic, uncharacterized neutron flux environment deep within its structure, a localized region of extreme nuclear activity far beyond what surface temperature and luminosity would predict. A minority of researchers have gone further, suggesting that if the nuclear environment inside Przybylski's star is genuinely capable of synthesizing transuranic elements at observable rates, it may represent a class of stellar nuclear process that current models do not contain a slot for. The star is not misbehaving. The star is doing something. We simply do not have the physics to describe what. What is producing Einsteinium inside a star that has no business producing Einsteinium? Why are the decay products of these short-lived elements not dominating the spectrum if continuous production is occurring? Is atomic diffusion, even in its most extreme theoretical form, capable of behavior this far outside its documented range? And if some unknown nuclear mechanism is operating inside HD 100 and 1065, continuous, energetic, transuranic, why is this the only star we have found it in? Not far from this mystery in the catalog of extreme stellar objects, though vast distances removed in the brutality of what it represents, a pulsar, spinning 700 times per second, is carrying a secret in its mass that may be just as difficult to explain. PSR J0952-0607. You are holding very still. Not because you've been told to, because something in the data on the screen in front of you has made movement feel inappropriate. You are at the Green Bank Observatory in West Virginia, and it is 2022, and the number printed at the top of the readout is 2.35. 2.35 solar masses, packed into an object roughly 20 kilometers across, and that object is spinning, not slowly, not at some dignified astronomical rate. It is completing 707 full rotations every single second. You stare at the number, you check the pipeline, you check it again, the number does not change. This shouldn't exist. Here's what makes this impossible. The Tolman-Oppenheimer-Volkoff limit, the theoretical maximum mass a neutron star can sustain before its own gravity overwhelms the degeneracy pressure holding it apart and collapses it into a black hole, sits somewhere between 2.2 and 2.9 solar masses, depending on the equation of state model you trust. PSR J0952-0607 sits at 2.35. It is not comfortably below that limit. It is pressing against the interior of it, hard, like something testing the walls of a room it was never supposed to fit inside. The discovery was published in the Astrophysical Journal Letters in 2022, led by Roger Romani of Stanford University, and a team of researchers using the Keck Observatory on Mauna Kea in Hawaii. What they found confirmed and extended earlier timing measurements of the pulsar, a millisecond pulsar located approximately 3,000 light-years from Earth in the constellation Sextans. 3,000 light-years sounds manageable until you sit with it. Light, traveling at 300,000 kilometers per second, takes 3,000 years to cover the distance between us and PSR J0952-0607. The light arriving at Keck's mirrors tonight left that system roughly 1,000 years before the first stones of any European cathedral were laid. And the object those photons departed from is rotating 707 times per second. To place that in the body, if you could stand on the equator of PSR J0952-0607, which is about 60 kilometers in circumference, the surface beneath your feet would be moving at roughly 70,000 kilometers per second. Roughly 24% of the speed of light. The centrifugal forces trying to fling matter off the equator are almost unimaginably violent, and yet the star holds. The gravity is stronger, the interior is dense enough, strange enough, to resist. PSR J0952-0607 belongs to a class called Black Widow pulsars. It has a companion, a low-mass star that once orbited it in a gravitational dance, and for billions of years, the pulsar has been consuming it, stripping away hydrogen through accretion, feeding that mass into itself, using the infalling material to spin faster and faster, a process called recycling. The companion is now a desiccated remnant, a brown, shriveled near nothing less than 1/50th the mass of Jupiter, being slowly devoured by the thing that used to orbit alongside it. The pulsar has grown bloated and ferocious on the corpse of its partner. The standard cosmological model says this process, spin up through accretion, is well understood. Millisecond pulsars are among the most precisely timed objects in astrophysics. Their rotations are more regular than atomic clocks. The mainstream consensus holds that a sufficiently massive neutron star, spun up by accretion, can approach but not cross the collapse threshold. The equation of state of neutron star matter, the relationship between its density and pressure, provides a hard ceiling. When you exceed it, you become a black hole. The model is not ambiguous about this. But here is where the model begins to sweat. 2.35 solar masses is a measurement with a margin of error. Romani's team calculated it at 2.35 plus or minus 0.17 solar masses. That upper bound pushes the object into territory that some equations of state simply cannot accommodate, regions where the math produces black holes, not stable neutron stars. Some astrophysicists suggest that the interior of PSR J0952-0607 may not be made of ordinary neutron matter at all. A minority of researchers propose that at sufficient densities, neutrons dissolve into their constituent quarks, forming a quark-gluon plasma, a state of matter that existed in the universe's first microseconds after the Big Bang, and that this exotic interior phase is what allows the star to remain stable past the conventional threshold. Others argue the current equations of state are simply wrong, that we have never correctly modeled what happens at the center of the densest stable objects in the universe, because we have never had instruments capable of testing it. What we do know is this: PSR J0952-0607 should not be here, and yet every 707th of a second, it is. What is actually happening in the final 20 kilometers of a neutron star's core, where densities exceed anything reproducible in any laboratory on Earth? If quark matter exists inside PSR J0952-0607, does that change our understanding of matter itself, not just of stars, but of the fundamental constituents of everything? How close to the edge of collapse can an object spin before the rotation itself becomes part of what holds it together? And if the Tolman-Oppenheimer-Volkoff limit is wrong, what else in our model of stellar death is wrong beside it? The universe has spent billions of years building something at the absolute boundary of what matter is permitted to be, and just over 3,000 light-years away, something with almost no mass at all is doing the same thing in reverse, starving slowly at the edge of an impossible companion. SDSS J102915 plus 172927. You are standing at the edge of a forest that cannot exist. Every tree around you grows from soil, rich, dark, complex soil, layers of minerals deposited by a billion years of geological process. You know this. You have always known this. Trees need soil. That is not a preference. That is a physical requirement built into the biology of trees at the molecular level. And then you look down. The ground beneath this forest is bare rock, primordial granite, not a trace of the minerals that trees require. No nitrogen, no phosphorus, no calcium, nothing. Just the raw stone of the early Earth, untouched and chemically simple, exactly as it was the day the planet cooled. The forest stands there anyway, completely indifferent to your understanding of botany. That is what SDSS J102915 plus 172927 is. Except the forest is a star, and the bare rock is the chemical composition of the universe 13 billion years ago. In 2011, astrophysicist Elisabetta Kaufau of the Leibniz Institute for Astrophysics Potsdam and the Paris Observatory led a team that published their analysis of this star in the journal Nature. They had identified the object initially through the Sloan Digital Sky Survey, the massive photometric and spectroscopic mapping project that has cataloged hundreds of millions of celestial objects across roughly a third of the sky. But the Sloan data only flagged the star as unusual. To understand what they were actually looking at, Kaufau's team turned to the European Southern Observatory's Very Large Telescope at Paranal, Chile, deploying the X-shooter and UV spectrographs to dissect the star's light with extraordinary precision. What the spectrographs returned stopped them cold. SDSS J102915 plus 172927 sits approximately 4,500 light-years from Earth, inside the Milky Way's halo, the ancient, sparse, spherical cloud of old stars that surrounds the galactic disk like a ghost of the galaxy's earliest era. The star is small. Its mass is approximately 0.8 solar masses, and it burns cool and dim with a surface temperature of around 5,800 Kelvin. By itself, none of this is remarkable. Halo stars are typically old. They are expected to be chemically simple, but not this simple. The metallicity of SDSS J12914 plus 172927, the astronomical term for the abundance of all elements heavier than hydrogen and helium, is the lowest ever measured in a surviving star. Every element heavier than helium combined constitutes less than 1/6 millionth of the star's total mass. In the formal notation astronomers use, the star's iron abundance is below -4.8 on a logarithmic scale relative to the Sun, which means it contains less than 1 part in 60,000 of the iron our own Sun carries. Carbon, nitrogen, and oxygen, the elements that would normally be detectable even in extremely metal-poor stars, are absent at measurable levels. The star is, by every chemical metric available, essentially made of nothing but the hydrogen and helium that emerged from the Big Bang. Here is what makes this impossible. The standard cosmological model says that stars form when clouds of gas and dust collapse under their own gravity, compressing until the core reaches the temperatures required to ignite nuclear fusion. But gravity alone does not determine whether a cloud collapses. The cloud must also cool. As it compresses, it heats up. For collapse to continue, the cloud must shed that heat, and it does so primarily by radiating energy away through the quantum transitions of heavy elements: carbon, oxygen, silicon. These elements act as a thermal exhaust system for the collapsing cloud. Without them, the gas heats faster than it can cool, the pressure builds, and collapse stalls. The cloud disperses back into the void. No star forms. This is not a theoretical preference. It is a thermodynamic constraint embedded in every credible model of early star formation. The minimum mass threshold for stellar collapse in a chemically pristine cloud, known as the Jeans mass, is calculated to require the cooling assistance of at least some heavy elements. Below a certain metallicity, sometimes called the critical metallicity threshold, the physics simply does not permit stars of this size to form. SDSS J102915 plus 172927 is below that threshold, significantly below it. The mainstream scientific consensus offers one potential resolution. The critical metallicity threshold may be lower than current models predict. Fine dust grains, even in vanishingly small quantities, could provide just enough cooling surface area to allow collapse to proceed. Caffau's team themselves acknowledged this possibility in the Nature paper. The star might be sitting right at the absolute lower boundary of what is physically achievable, a single data point at the extreme edge of the possible. But that explanation demands that the physics worked out perfectly, precisely once, at exactly the limit of what the models grudgingly allow. It does not explain why we have found a star that appears to violate the threshold rather than approach it. It does not explain why where the dust came from in a universe that had barely had time to forge any heavy elements at all. Some astrophysicists suggest this star is not a first-generation object at all, but a second-generation star formed from gas that was minimally enriched by a single prior stellar explosion, a pristine inheritance from the universe's first few 100 million years. Others propose that our models of the critical metallicity threshold are simply wrong, that primordial star formation operated by rules we have not yet written down correctly. The star does not offer clarification. How did this gas cloud cool? What ignited it? Are there other stars like this, even older, still undiscovered in the halo? Is the critical metallicity threshold a law, or just our best current guess dressed up as one? And if the first stars formed in ways our physics cannot yet account for, what else from the universe's beginning are we misreading? From a star that should not exist, we turn to a system that seems to exist as several contradictory things at once. SS-433, a stellar object simultaneously firing jets of matter in opposite directions at a quarter of the speed of light. An engine whose power source remains one of the most contested questions in high-energy astrophysics. SS-433. You're not looking at a signal. You're watching something move. It's the late 1970s. The Very Large Array is not yet complete, but interim baselines are operating across the New Mexico desert, and radio astronomers are pointing their dishes toward a point in the constellation Aquila, catalog designation W50, a supernova remnant already known to be unusual. What comes back is not the steady hiss of a dying stellar shell. What comes back is a pair of emission lines that should not be where they are, and more unsettling, they are moving, week to week, measurably, systematically, back and forth across the spectrum like something breathing. Bruce Margone at the University of California, Los Angeles, published the first detailed analysis in the Astrophysical Journal in 1979. He called the object's behavior, in the careful understatement of a man staring at something he cannot classify, unprecedented. That word has aged with remarkable accuracy. What Margone and his collaborators had found, though its full architecture would take years to assemble, was a binary star system sitting approximately 18,000 light-years from Earth. 18,000 light-years. Hold that number for a moment. A photon leaving SS 433, when the last great ice sheet still covered northern Europe, would only now be arriving here. And across that distance, what we are detecting with absolute clarity is this: a compact object, almost certainly a stellar mass black hole, or possibly a neutron star, is actively consuming material from its companion, a supergiant star estimated at somewhere between 10 and 20 solar masses, and in doing so, it is launching two opposing jets of plasma outward at speeds that should not be physically achievable in this environment. Here's what makes this impossible. Those jets are moving at 26% of the speed of light, not an estimate, not a model output, directly measured Doppler velocity, approximately 78,000 kilometers per second, confirmed through decades of optical, radio, and X-ray observation by facilities including the Rossi X-ray Timing Explorer, the Chandra X-ray Observatory, and the European Space Agency's XMM Newton satellite. At that velocity, relativistic effects become non-trivial. The jet material is not plasma misbehaving. It is plasma obeying special relativity while simultaneously being launched from an accretion disk that, by any standard model, should not have enough coherence to sustain this. The jets are not chaotic. They are not diffuse. They are collimated, continuous, and they carry enough kinetic energy that over thousands of years, they have visibly deformed the surrounding supernova remnant, W50, into an hourglass shape, nearly 200 light-years across. But it is not the speed that breaks things, it is the motion. Those jets precess, they rotate in a slow cone, tracing a helical corkscrew pattern through space, completing one full precession cycle every 162 days. 162 days, with a precision that rivals an atomic clock, consistent across decades of observation. This is not drift, this is not noise, this is a machine. Something is driving that precession with an almost mechanical regularity, and the number, 162 days, has never been satisfactorily reproduced from first principles by any accretion disk model in 4.5 decades of trying. The standard cosmological model says that accretion disk precession in a binary system is driven by the gravitational torque of the companion star acting on a tilted, misaligned disk, a process called lens-thirring precession, or in simpler geometric terms, a nodding disk. The companion's gravity tugs the disk into a wobble, the wobble drives the jets trace the cone, and the period emerges naturally from the system's orbital mechanics. This is a legitimate, well-developed theoretical framework. It is not fringe. Several research teams, including work published by Sergei Fabrika of the Special Astrophysical Observatory of Russia in his comprehensive 2004 review in Physics Uzbeki, have applied it seriously and with mathematical rigor. But the data doesn't support this. Not completely. The predicted periods from disk precession models consistently diverge from the observed 162 days, unless specific parameters are tuned in ways that other observations of the system don't independently verify. The disk's physical extent, the mass transfer rate, the compact object's spin, none of these constrain naturally to produce the observed number without circular reasoning. Some astrophysicists suggest that the precession period may be locked to the binary orbital period through a resonance mechanism that isn't yet understood, a kind of gravitational clock embedded in the system's architecture. A minority of researchers propose that the compact object itself, if it is a black hole, may be contributing frame-dragging effects from its own spin to the precession geometry in a way that current models treat as negligible, but perhaps should not. What no one has done is calculate the right answer from the known quantities and arrive at 162 days without already knowing the answer first. What is actually holding those jets in their cone? What tunes the precession period to that exact number and keeps it there across decades of observation? If the disk model cannot reproduce this without adjustment, what is the adjustment hiding? Is there something about the angular momentum transfer in relativistic jets that physics has not yet formalized? And if a system 18,000 light-years away can do this with such mechanical precision, how many others are doing it in silence beyond our current resolution? From a black hole spitting matter at a fraction of the speed of light, in a pattern that defies its own theoretical explanation, we turn now to something quieter and stranger, a dying star not ejecting plasma, but exhaling carbon into the dark, and doing it in a geometry that should not exist. IRC plus 1021-6. You are standing in a garden made of gas. That is the only way to describe it. Concentric rings, each one a perfect halo of carbon dust and molecular gas, nested inside the next, like the rings of a cut tree trunk, like the grooves of an ancient record, like something that was meant to be read. You are looking at the infrared composite from the Hubble Space Telescope, taken as part of a long baseline observational campaign and published in Astronomy and Astrophysics. In 2010, and what you are seeing, what the data is insisting you see, is not chaos. It is not the random violence of a dying star throwing itself apart. It is rhythm. It is intervals. It is, impossibly, something that looks like schedule. At the center of this garden, barely visible through layers of its own expelled atmosphere, is IRC plus 10216. It is 490 light-years away, not a cosmological distance, almost neighborly by the standards of this series. 490 light-years means that the light you are receiving left this star sometime around 1533, when Nicolaus Copernicus was still alive, still working, not yet ready to tell the world that the Earth moves. And in that time, in the time it took that light to cross the gap between that dying star and this instrument, nothing about what IRC plus 10216 is doing has become any easier to explain. It is a carbon star. More precisely, it is an asymptotic giant branch star, a star in the final chapters of its life, a star that has exhausted its hydrogen and helium core reserves and is now burning in shells around a dense, cooling core of carbon and oxygen. Its surface temperature sits at around 2,300 Kelvin. To call it a red giant is almost an understatement. Its luminosity is approximately 8,800 times that of the Sun. Its radius, depending on the measurement baseline, is somewhere between 400 and 500 solar radii. If you placed it at the center of our solar system, it would swallow Mercury, Venus, Earth, and Mars, and it would be seriously considering Jupiter. It is losing mass at a ferocious rate, approximately 1.5 times 10 to the negative 5 solar masses per year, meaning it is effectively exhaling itself into space. This outflow is one of the most studied in stellar astrophysics. Researchers including Jérôme Petit, José Cernicaro at the Spanish National Research Council, and Lucy Zuris at the University of Arizona have spent decades cataloging the molecular complexity of this outflow, detecting over 80 distinct molecular species in the circumstellar envelope, including water, ammonia, and organic molecules that, in other contexts, we would associate with the building blocks of life. But the chemistry is not what breaks the model. The shells are what break the model. In 2015, a high-resolution study combining data from the Hubble Space Telescope and the Institut de Radioastronomie Millimétrique Array in France identified over 500 discrete concentric shells of gas surrounding IRC plus 10216. 500. Each shell represents a discrete episode of enhanced mass ejection. Each shell is spaced roughly 800 years apart from its neighbors. The spacing is not approximate. It is not a loose average. It is consistent to a degree that has prompted sustained and unresolved debate in the stellar physics community. Here is what makes this impossible. The standard cosmological model, or more precisely, the standard model of asymptotic giant branch stellar evolution, says that mass loss from dying stars is driven by radiation pressure on dust grains, modulated by thermal pulses occurring deep in the stellar interior. These thermal pulses, sometimes called helium shell flashes, occur when the helium-burning shell around the core periodically ignites, releasing energy in a burst that drives enhanced mass loss. The predicted interval between these pulses, for a star like IRC plus 10216, is somewhere between 10,000 and 100,000 years. The shells are spaced 800 years apart. That is not a rounding error. That is an order of magnitude discrepancy, possibly two. The mainstream explanation, at its strongest, accounts for larger-scale structural variation in the envelope. It does not account for 500 shells separated by 800 years with the kind of regularity that, if you plotted it, would look less like a stellar death rattle and more like a signal deliberately encoded in gas. But the data doesn't support dismissal either. Some astrophysicists suggest that a binary companion, an unseen star orbiting inside or just outside the envelope, could impose a periodic gravitational perturbation on the mass loss rate, creating regular density enhancements in the outflow. A minority of researchers propose that previously unmapped oscillation modes within the stellar interior itself could drive pulsations on timescales far shorter than conventional thermal pulses predict. Neither explanation has been confirmed. Neither has been ruled out. What we are left with is a star 490 light-years away that has been keeping time, precise, consistent, inexplicable time, for at least 400,000 years. Was the clock always there? Is it internal or imposed? Is the mechanism one we have the mathematics to even conceive of yet? And if a dying star can maintain this kind of periodicity over timescales that dwarf recorded human civilization, what does that say about what we think we know about the lives of stars? The universe offers no answers, only signals. And sometimes the signals are so precise, so patient, so eerily measured across the dark that the silence around them becomes the most unsettling data of all, which is exactly where we find ourselves now, looking back across 10 objects that each, in their own way, handed us the same note. You are missing something fundamental. What these 10 objects share is not a category. They are not a list. They are a pattern. And the pattern is this. Every time we have built a framework large enough to contain the universe has produced something that will not fit inside it. Betelgeuse pulses on a rhythm no stellar model fully predicts. R136A1 exists at a mass that its own radiation pressure should have prevented. Tabby's star dims in ways that 72 competing explanations have failed to settle. The Methuselah star is older, by every measurement we trust, than the cosmos that supposedly produced it. SGR 1806-20 released more energy in 0.2 of a second than our sun will produce in 250,000 years. Przybylski's star contains elements with half-lives measured in days, sitting calmly in a stellar atmosphere that has no mechanism to put them there. PSR J0952-0607 spins at 707 rotations per second and should not be spinning at all. Caphaw's star formed from almost nothing and survived anyway, rewriting what we thought primordial chemistry required. SS433 fires jets of plasma at a quarter of the speed of light in directions that precess like a cosmic gyroscope no one ordered. And IRC plus 10216 breathes carbon molecules into interstellar space, molecules that, by every account, should never have formed at all. Taken alone, each of these objects is an anomaly. Taken together, they are something else. They are the universe telling us, repeatedly and at enormous scale, that our models are maps, and that maps are not the territory. The standard cosmological framework is not wrong. It is incomplete. And incompleteness at this scale, stretched across billions of light years and billions of years of cosmic time, is not a small thing. It is a structural feature of our ignorance. Every solved anomaly has historically concealed a deeper one underneath it. There is no reason to believe that pattern has ended. The universe is not waiting to be understood. It is not arranged for our comprehension. These stars, ancient, impossible, violent, quiet, dying, spinning, breathing, were doing these things long before any mind existed to call them anomalies. They will continue long after our frameworks have been revised, discarded, and revised again. We look up, we measure, we name, and the cosmos, vast and indifferent and strange beyond any model we have ever built, simply continues.